Hello. Now we'll study some more properties of current. So in the previous lecture we learned this is the formula to calculate the current, where it is the time rate of flow of net charge, and the net charge should be the positive charge. Okay. Now the property of the current we are interested right now is regarding whether it is a scalar or it's a vector. So as far as we are concerned, the current for us, current is a scalar quantity. Scalar quantity. The more appropriate word will be it is not a vector. So the thing is, if we talk about the current, in this case, it does not follow the vector addition law. The current does not follow vector addition law. So because of that, current is not a vector quantity. So current is not a vector quantity. So when we want to calculate the current, we can follow the scalar addition principle for adding it. So if the current is moving in the same directions, then we can just add them. If it is moving in the opposite direction, we can just take the difference about that. So it's a scalar quantity. Okay. So when we go calculating the value of current in a conductor, so if there is a linear conductor and it is having a cross-section area A, the cross-section area of this linear conductor is A. And let's say this linear conductor, it is carrying the charge density N. The charge density inside this linear conductor is N. So it is a charge density. And I'm talking about the positive charge density per unit volume. The density I'm talking about is the per unit volume. So in one unit volume, there are n number of charges inside this conductor. The cross-section area is A. And if each and every electron is moving with velocity Vd, so there are electrons, or there can be positive charge particle, I'm calling that Q. So there are charge particle which is carrying a charge Q, and they are moving with velocity Vd. They are all moving in the same direction. So basically we are talking about the net movement. So as you know, in the previous lecture we talked about there will be some charges which will be moving from left to right, and there will be some charges which will be moving from right to left. Okay, so what we do, we take the net. So if 10 number of charges are moving towards the right and the 8 number of charges are moving towards the left, for me, I'll say there are 2 charges which are moving from left to right. So that's the number I'm talking about. And those charges are moving with velocity Vd, and this is known as drift velocity. What is drift velocity? We will learn that in later lectures. So the charge particles, they are moving with velocity Vd. They are crossing the cross-section area A, and n number of charge particles are there in 1 unit volume. Okay. So when we define, in this case, if we want to calculate the current, the value of current in this case, if we want to calculate that, the value of current here, it will be NEA Vd. The value of current flowing in this conductor will be equals to NEA Vd, where N is charge density inside this conductor. E, I'm taking the electron, E can be Q as well. It is the value of charge, individual charge particle. In majority of cases, this value is equals to E, because the majority of conductors, the particles which are moving are electrons. So, but I'm saying they are the particles are carrying a charge Q. So I'm taking the value Q. So NQA Vd, Q is the charge particle carried by single particle. A is the cross-section area of this conductor, and Vd is the drift velocity. So in case of linear conductor, that's how I'll calculate, and we will calculate the current. Okay. What if I'm not having a linear conductor? What if I'm having a circular conductor? So if I'm having a circular conductor, like I'm having a circle, the conductor is circular, and again it is carrying n number of charge particles per unit volume, and the charge particles which are carrying a charge Q. But these charge particles are revolving in a circle. Basically, if this conductor, if I cut, it is a linear conductor, but I'm making it a circular. So these charge particles are moving in a circular ring shape. Okay, and these charge particles, they are moving with velocity Vd, or we can say they are rotating with angular velocity omega as well. The thing is, we are doing this so that we can calculate the current in case of atoms. So you see, in case of atoms, there are bound electrons, valence electrons, and these electrons keeps revolving around the circuit in a defined path. So in that case, basically we don't need conductor. It can be the conductor we need so that the charged particle can be provided the path. If the charged particle is revolving in a circle without the need of this conductor, we don't need this conductor. All we need is a charged particle. Okay, so in that case, this will be omega. So these charged particles, they are moving with velocity Vd, or we can say they are revolving with velocity, angular velocity omega. And the radius is given as r. Since you know, in this case, Vd can be written as r omega. Because Vd is the velocity here and the omega is the angular velocity here. And this omega can be equated with 2 pi by t, or we can say 2 pi nu, where t is the time period of the rotation and the nu is the frequency of the rotation. And in this case, if we want to calculate the current, so the cross-section area is A. Again, we'll use this principle. Okay. So the current we define as the charge flowing through this cross-section area, total charge flowing through this cross-section area. That's how we define. Okay, in 1 second, or we can say delta t time. So if it is having a n number of, the density is n, and you see this time period. This time period is defined as the time required to move once. So in this time capital T, since this T is the time period of this rotation, in this time T, we can easily say that electrons are revolving. Electrons have performed one rotation, and only the one rotation. So if this is my cross-section area, then I can say that within time capital T, within this capital T time, each and every charged particle in this conductor would have crossed this cross-section area only once. Not twice, only once. So see, when the movement is not happening, these charged particles are occupying this space. These charged particles are occupying this space at t0. And when you will see the structure at t is equals to capital T, the structure will be same. Because you see, this charged particle in capital T time will perform one complete rotation. So after completing one rotation, it will reach here. This charged particle also within this time will perform one complete rotation, it will come here. This charged particle will also perform one rotation, it will come here. This charged particle will also perform one rotation and it will reach at this point. So within this time, each and every charged particle will be crossing this cross-section area only once. Okay, so the total charge crossing this cross-section area within this time will be equals to n, which is the total number of electrons here, multiplied with charge. So delta Q value will be equals to n times of Q. Because n is n is not the density, n is the total number of charges. N is the total number of charges. So since n number of charges are there, and in this time, each and every charge will cross this cross-section area only once. And each charge carries the charge Q. So that much charge will be crossing this cross-section area within delta T time. And delta T here is capital T. So current in this case will be equals to NQ divided by capital T. Okay. And this capital T, we can replace the capital T by omega also. So this value, if we want, this value of current can be written as NQ divided by 2 pi by omega, or it can be said that NQ omega upon 2 pi. Or if you want the value in terms of Vd, that also we can get. Then I will be equals to NQ Vd upon 2 pi r. You see, that's how we can define the value. Okay, so this is the current in a circular motion, these values. Generally, this principle we use for the electron, movement of electron around the nucleus, which is generally in this case. And when we talk about the electron in the valence shell, then electrons, number of electrons in the valence shells are fixed, because if it is a S shell, number of electron will be 2. If it is P, it will be 6. It is D, it will be. That's how it will go. So the number of electron in those shells, which is a fixed shell, we can assume it to be circular, perfectly circular. The number of electrons there are fixed. The value of n is fixed in those cases. That's why we have considered here the number of charges. Here the charge density we have taken, here the number of charges we have taken. Okay, so that value, with the help of that value and with the value of omega, which generally you can calculate using the Bohr model, you can calculate how much current equivalent is flowing in that circuit, which is a atomic circuit. Okay, so this is for circular motion, and this is for linear motion. For linear motion, that's how we define the current value. Okay, thank you.